A big part of a college algebra class is getting introduced to the different types of relationships we see in math. The most basic is a linear function, which only has plain x's. But once you get past those, the next step is to a quadratic function, which has x squareds. There's a lot to learn about quadratics, but the best place to start is with their graphs. Anytime you graph a quadratic equation, you end up with what is called a parabola. Parabolas have been behind the scenes of sports, celebration, and wars for ages. When the first javelin was thrown in the Greek Olympics, or when the first firework was launched in China, or even when the first cannon was fired in the Civil War, they all flew through the air in the shape of a parabola. Today, parabolas are still around in things just like this, but they've also made their way into more modern inventions like video games. Back around 2007, I actually had an idea for a video game that would use parabolas. I thought it might be fun to just shoot things across the screen, so what if these birds had their eggs stolen by some pigs, and the birds got really angry and wanted to get back at the pigs to get their eggs back? Maybe we could, I don't know, shoot the birds across the screen, these birds that are really angry, with a slingshot, and see if we could attack the pigs and get our eggs back. So here we've got a likely scenario. Let's try to launch our bird that's really angry at that mean old pig and let it fly. We missed. Okay, let's try again. I want to aim up a little bit more this time. Let's try it again. And yeah, we got him. The game draws in those little dots to help you aim your shots, but the path they sketch out is actually a perfect parabola. Notice that depending on the angle we launch the bird at, we get a slightly different shape. But even if we shot the bird almost straight up, or even really close to the ground, it would actually still be a parabola, because there are lots of different kinds. Depending on how we shoot the bird, each parabola would have a different maximum height, which is our first vocabulary word. The maximum is the highest y value that the parabola reaches. In this case, that represents the height that the bird gets. The name of the actual point on the parabola where it gets to the maximum is our second vocab word. It's called the vertex. You might say that the vertex is in the middle of the parabola. That's because parabolas are symmetrical. They're the same on either side. This means our third vocab word is the line that goes straight down through the middle of the parabola to divide it in half. It's called the axis of symmetry. Just like any other graphs, parabola's intercepts are where the curve intersects either the x or the y axis. In parabola word problems, the x-intercepts will often be the place where your flying object hits the ground, just like here. These x-intercepts of quadratic equations, and also bigger functions, can also be called roots. For our last few vocabulary terms, we'll need to abandon our video game analogy, or maybe imagine a new version on some crazy backwards planet where gravity is upside down. This is because parabolas can be concave down, like the examples we've been talking about, or concave up, which means the whole shape is just flipped upside down. All the vocab we've talked about is exactly the same for concave up parabolas, except one. Now, instead of our vertex being a maximum, they indicate the minimum that the parabola will reach. To review, parabolas are the shape that graphs of quadratic equations take. They look kind of like big letter U's and happen anytime something is launched into the air. They can be concave up or concave down, have vertices where a maximum or minimum happens, intercepts where they cross one of the two axes, and an axis of symmetry that divides them in half.
A quadratic is a polynomial of degree 2. That's one whose highest degree term is a times x squared. The graph of a quadratic function is a parabola. The parent function is y equals x squared. There's a point on the parabola right at the tip that's called the vertex. For the parent function, this is the lowest or the minimum point. The range of the parabola, the range of the quadratic function for the parent function goes from the vertex on up to positive infinity. Therefore, the range for the parent function is y, such that y is greater than or equal to 0. In addition to the vertex, there's a feature called the axis of symmetry. It's a line that divides the parabola in half, goes vertically through the center of the parabola. Now, if we move the parabola, the vertex and the axis of symmetry, of course, are going to move with it. We want to focus on the x-intercepts. These exist where the graph crosses the x-axis. This could be in two places as shown, could be in one place, or it might not happen at all. These are also called the zeros, the solutions, or the roots of the equation. If the graph is reflected, the vertex becomes the highest point, the maximum, and therefore the range is going to start from the vertex and go downward. And finally, the domain of the quadratic function is going to be all real numbers. Any number could be plugged in for x. It's important to understand both the standard and the vertex forms of the quadratic equation. Both forms tell us important things about the function and its graph. The standard form looks like this. The numbers that are important here are the a, the b, and the c. These help us to find the factors of the function. The vertex form is also very useful because it helps to tell us about where the graph is located. Notice that this looks like the familiar transformed parent function kind of format, where we have a plus or minus sign out front that tells us whether we have reflection or not. We have a value a that multiplies the x squared term. If a is greater than 1, we have vertical stretch. If it's less than 1, we have vertical compression. And if a is not there, meaning that it's equal to 1, then we have neither stretch nor compression. The h value gives us horizontal shift. So if we're adding h, we shift left. If we're subtracting h, we shift right. And the k value at the very end there shifts up or down depending on whether k is positive or negative. Switching back and forth between the two forms, from the vertex to the standard form is fairly simple. Just multiply everything out. You're going to have to FOIL the x minus h squared as x minus h times x minus h. And you can convert from the standard to the vertex form by finding the value of h, which is going to be negative b over 2a, using the values from the standard form. Then you find k by plugging this h value in place of x. Another way to do this is using a graph. You can graph the function in standard form, then find the vertex coordinates using the calculator's minimum or maximum function. The x-coordinate is h and the y-coordinate is k. Then take the a value from the original standard form, along with the vertex coordinates that you found, h and k, and write the function as you see listed there. Here's an example. This graph has a vertex, the maximum point, at 3, 1. Here's the graph of negative 2x squared plus 12x minus 17. We see that since the vertex is at 3, 1, h is 3 and k is 1. We'll take the a value from the standard form, which is negative 2, and then so the vertex form becomes negative 2 times x minus 3 squared plus 1. Just filling in a, h, and k. Factoring quadratics is very important. What factoring means is to find the two binomials that multiply together to create the quadratic. So for example, if we have the quadratic x squared plus 3x plus 2, that can be factored into two binomials, x plus 2 and x plus 1. This helps us to find the zeros, or the x-intercepts. For example, if we're analyzing how far a kicked football is going to travel, we might want to know where those points are. These 2 points would be the x-intercepts where y is equal to 0. So how do we do this factoring thing? Well, one thing we have to remember is the zero product property. And all this means is that if 2 or more factors are multiplied, 2 or more things are multiplied together, and the answer becomes 0, that means that one or more of those factors has to be 0. Anything times 0 is going to be 0. So, from the previous example, if x plus 2 times x plus 1 equals 0, then we know that either x plus 2 equals 0 or x plus 1 equals 0. So for x plus 2 to be equal to 0, x has to equal negative 2. And for x plus 1 to equal 0, x must equal negative 1. So therefore, the x-intercepts, or the roots, zeros, or solutions, whatever you call them, are going to be the set of numbers negative 1 and negative 2. So how do we go ahead and find these factors? Well, to factor a quadratic, no matter which method that you use, you want to rewrite the quadratic in standard form. And you want to write it so that you have everything on the left side of the equation equal to 0. Move everything to the left by adding or subtracting so that only 0 remains on the right side. For example, if you have x squared minus 5 equals 2x, subtract 2x from both sides to make the right side 0, and you get x squared minus 2x minus 5 equals 0. Another example that you see there, we're going to add 2x squared and 7 to both sides to get the result that you see. So let's go ahead and try out these different methods to factor the quadratic. The easiest, perhaps, is to use a graph. Okay, we're going to go ahead and just graph the quadratic, and we're going to find the x-intercepts. Now, depending on how much accuracy you need, you can look at this and say this is at 2, and this appears to be at minus 4. So you know that your x-intercepts are 2 and minus 4. If you want to be a little bit more precise about it, on the calculator you want to go to Menu, Analyze Graph, and 0. This will find the x-intercepts, or the zeros, automatically for you. Click to the left and then to the right of each x-intercept. And then finally you're going to get the values, negative 4 and 2, that the calculator provides for you. Once you have those numbers, we know that x equals negative 4 is true when y equals 0, so we can add 4 to both sides and get x plus 4 equals 0. So since that's equal to 0, we know that that's going to be one of the factors. Doing the same thing for x equals 2 gives us x minus 2 as the factor, the other factor. So we know now that the quadratic that we graphed, x squared plus 2x minus 8, is equal to those two factors multiplied together. And if you want to check it, you can go ahead and FOIL it out. Speaking of foiling, you can also factor by what we might call unfoiling. If you take this expression, x plus p times x plus q, and FOIL it, multiply it out, you get x squared plus p plus q times x plus p times q. Why that's important is because if you compare this to the standard form, you'll see that p plus q is the same as b, and p times q is the same as c. And so it becomes a matter of trying to find two numbers, p and q, by figuring out which two numbers are going to add up to give you b, and which of the same two numbers will multiply to give you the c number. So for example, if you take x squared plus 2x minus 8, you see that we're looking at 4 and negative 2 as possibilities here. We can check that by saying that to add them together, 4 plus negative 2 gives us b equals 2, and 4 times negative 2 gives us negative 8, which is our c value. So since the sum adds up to 2, and that's what we're looking for here, and the product adds up to, or multiplies out to negative 8, and that's what we have here, we know that those are our factors. So we just do the same thing. X plus 4 is going to equal 0. X plus negative 2 or x minus 2 will equal 0, and therefore those are the factors. Now this only works when a equals 1, and sometimes finding the p and q numbers isn't really all that easy. So this does work a lot of times for some of the simpler ones. If not, we can use the quadratic formula. Now this is something that always works, but it involves a formula that's pretty easy to mess up when you use it. So you do have to be careful. First of all, be sure that your quadratic is in standard form equal to 0. So the two values then are found using these two equations. Notice that most of the time you're going to see the quadratic formula written with a plus minus here. I've just split them up into two so that we can separate the two answers. One is found by adding the two terms in the numerator, and the other is found by subtracting the two terms. So for example, if we have x squared plus 2x minus 8 equals 0, we can see that the a term is non-existent, which means that it's actually 1 times x squared. The b term is 2, and the c term is negative 8. Plugging all those numbers in, we get x1 is equal to 2. Now, what I was saying before, it's easy to mess up because you have to get this put into the calculator exactly correctly, or you'll get the wrong answer. So in this case, we get x equals 2, which means that if we add negative 2 to both sides, we get our factor x minus 2 equals 0. Doing the same thing for x2, we see that that's equal to negative 4. And those are the same answers we got before. Now let's focus on something called the discriminant. Now remember, we can't take the square root of a negative number, so what if all that stuff inside the square root, b squared minus 4ac, turns out to be negative? Well, this thing inside the square root is called the discriminant, and that's because it discriminates between three possible cases for the solutions. One is that the discriminant is going to be positive. In this case, we're going to have two real roots. The parabola of the graph is going to cross the x-axis in two places. If it's exactly equal to 0, we're going to have one real root, which we sometimes call a double root. That means that the graph is going to only touch the x-axis in one point. And then finally, if we have the discriminant less than 0, if it's negative, we're going to have two roots that we call imaginary. So if you have two real roots, the graph of the parabola is going to cross the x-axis twice. These two roots become the factors that you see there. So for example, right here we see we cross at positive 2, so x equals 2 is a root, and so if we set that equal to 0, we see x minus 2 equals 0. That becomes one of our factors. Same thing here, x equals negative 4 gives us this factor x plus 4. Here's a case where we have one real root, which is what we might call a double root. And this is where the parabola just touches the x-axis in one point. That means that the two factors are really the same number. Both factors are going to be built from x equals negative 2. So they're both multiplied together like this. This is why that's called a double root. And finally, we have the case where we have imaginary roots. This occurs when the parabola doesn't cross or touch the x-axis at all. Now, this gives us a negative number in the square root on the quadratic formula, in the discriminant. And so we need to figure out how to work with that. And what we do is we look at the square root of a negative number as this thing I, this is called the imaginary operator, I times the square root of the number without the negative sign. So for example, if we have square root of negative 9, what we're going to do is take this negative sign outside and make it an I, and then we're going to have just the square root of 9. Square root of 9 is 3, so that gives us 3 times I. So it's possible then that our factor might look like something like this with all of these numbers in here, including this I. So anytime you see the I inside the factors, you're going to know that this parabola does not touch the x-axis anywhere. So let's see how we can find solutions from the calculator as well. Again, we're going to set the quadratic equal to 0 if it's not there already. Now this could be in standard form or in vertex form, doesn't really matter. On a calculator page, what you want to do is type C polyroots, just like you see it there with the parentheses opened. Now you're going to put in the quadratic and then comma x and then enter. You have to put the comma x to tell the calculator that that's the variable you're working with. It's going to give you a pair of solutions that are going to look like this. If the solutions that you see have an I in them, then you know that they're non-real. These are your imaginary roots. So for example, here's a calculator screen with all three examples. In the first example, we have a solution that consists of two real roots. -4, and 2. So when you put those factors together, you get x plus 4 and x minus 2 from the answer that's shown right here. In the next case, we have one single double root at x equals -3. Again, this gives you these factors, which suggests a double root, and that comes from the answer that the calculator gives you here. Finally, we have a quadratic that gives us two non-real imaginary roots. So you see the answer on the calculator looks pretty complicated, but we want to look and see if we have these I values in here. This indicates that these are non-real roots. So our x values for the roots are going to be these two numbers here. So let's just summarize real quick then. The vertex is the minimum or maximum point on the parabola, right at the tip. The x-intercepts are important points where the graph crosses the x-axis. So these are going to help us to factor and solve quadratic equations. The axis of symmetry divides the graph in half. The domain of all quadratics is all real numbers. We can always put any number for x that we want. The range is going to depend on which way the graph opens. If it opens up, we're going to go from the vertex upward to positive infinity for the range. And if it opens downward, we're going to start at the vertex and go downward to negative infinity. We can factor by graphing, looking for the x-intercepts, doing what we might call unfoiling, where we need two numbers that add up to b and multiply to c. We can use the quadratic formula, or if we have the Nspire calculator available, we can use C polyroots. And remember that a quadratic might have two real solutions. This would occur if the discriminant is greater than 0. It could have one real solution, which we would call a double root, if the discriminant is equal to 0. Or it could have no real solutions at all. These would be imaginary solutions if the discriminant is negative. Again, the discriminant will tell you how many roots you have of what kind.